So today what we're going to be talking about are reflections. We're still dealing with our transformations and ways that we can move shapes around on the plane. And so today we want to talk about reflection. A reflection is a transformation that flips a figure across a line. A reflection is flipped over a line. So if I have this arrow on the left-hand side of this line and I want to do its reflection, it's going to flip over that line and go to the other side of the line. Things to know about reflections is that they are the same distance from the line, just on the other side. It is a mirror image. Reflection is something that we're very used to. It's a mirror image of itself. You know, this is a concept that we have dealt with for a while. Since you're very young, you notice that things are backwards in the mirror. And so it's the exact same image, just on the other side of the line. So it's same, but it's backwards. All right. The line that a shape is flipped over is called its line of reflection. So it is whatever it is being reflected over. It is where we're measuring the reflection from. Notice the shapes are exactly the same distance from the line of reflection on both sides. So every point, this point is the exact same distance from the line, just on the other side. This point is the exact same distance from the line, just on the other side. So these points that were the furthest away from the line are still the furthest away from the line, just on the other side. The line of reflection can be on the shape, or it can be outside of a shape. So we can reflect something over a line even if the line goes through the shape itself. Determine if each set of figures shows a reflection or a translation. So would this be a reflection or a translation? A reflection or a translation. Now, this one, it's on the opposite side, but notice that it's not in the exact same spot. It moved over. If we move left to right, up and down, that's a translation. If we look at this triangle, B is directly across the line from B. They line up from each other. They're looking in the mirror at each other. They just happen to be flipped over in the other direction. Sometimes a figure has reflectional symmetry. This means that it can be folded along a line of reflection within itself so that the two halves of the figure match exactly, point by point. Again, symmetry is when something's the same on both sides, another term that we're familiar with. Reflectional symmetry just means that the line that it is being reflected over also happens to be a line of symmetry, meaning that it's the same on both sides. So basically, it's the idea that if you fold the shape in half, it matches up exactly, and then it's referred to as reflectional symmetry. So we'll fold it in half. Do you remember folding a piece of paper, drawing half of a heart, and then cutting it out? So you've got that folded piece of paper, you cut out the heart, and then when you unfold the piece of paper, you have a heart. It's the same on both sides. If I fold this in half, this is a reflected shape. This point is the exact same distance as this side. Like, this shape has been reflected to this side, but it is also symmetrical because it's exactly the same on both sides. So it has reflectional symmetry. The two halves are exactly the same. They are symmetrical. Reflectional symmetry means that a shape can be folded along a line of reflection so that the two halves of the figure match exactly, point by point. So it is a line of symmetry and it is a line of reflection. So a line created by the fold is the line of symmetry. A shape can have more than one line of symmetry. Where is the line of symmetry for this shape? So if we wanted to fold this shape in half and have it be the same on both sides, where would we have to fold it? If I folded it right here, I'd have like a square on this side, but I'd have an arrow on this side. It wouldn't be the same. If I were to fold it a long ways, see here, it doesn't work. Yeah, that doesn't work. But if we fold it long ways, along here, fold it over, okay, that way it matches up. It does have reflectional symmetry this way. So this would be a line of symmetry and a line of reflection. So how many lines of symmetry could each shape have? How many ways could we fold it and end up with the same shape? So for the triangle, notice if we fold it and touch two corners to each other, we could fold that triangle in half. It's basically going to make a little right triangle. Fold this one right there, and then if I take this corner to this corner, I can fold it right here. There's lots of ways we could probably fold this square. Take corner to corner or corner to corner. That's going to line up. Or fold it in half this way and get two rectangles instead of two triangles. So let's see. There was 3 for the triangle. We got 1, 2, 3, 4 for the square. Let's see. Ways that we could fold. If I touch this corner to that corner and fold it right along that line, that should line up. Oh, there's lots of lines for this one. Lines of symmetry. There were 5 for that one. Do you notice a pattern? These polygons, they're regular polygons, meaning that all their sides are the same and all their angles are the same. When you have regular polygons, however many sides you have is how many lines of reflectional symmetry that you have. Now, which of these flags have reflectional symmetry? Somewhere where you can fold the flag in half and it's exactly the same on both sides. No, that one's not. No matter how we fold it, having this in the upper corner makes it not the same, no matter how we look at it. But Canada, if I put a line right down the middle, the leaf matches up, the red rectangles match up, it has a line of reflectional symmetry. Again, the different colors kind of mess us up, and the eagle is too fancy. I might have been able to do it had the symbol not been there. This one, however, England, we've got it going both ways. So we have 2 for that one. Now, just like with translations, we talk about reflections on the coordinate plane. So we know that there has to be a rule for us to use with our points. With translations, we just had to add or subtract to the x and y coordinate, depending on which direction we wanted to move. When you do reflections on the coordinate plane, it depends on what line you're reflecting it over. So we have a couple of different rules that we're going to have to memorize. So we can do reflections on the coordinate plane over the axis. I can take a point and I can reflect it over the y-axis. So if this is the y-axis, I can reflect it over to the other side. So that means it's the same distance from the axis, just on the other side. I can reflect it over the x-axis. Flip it down to go beneath the x-axis. Same distance, just on the other side. So our rules for reflecting over the x-axis, if I'm reflecting it over the x-axis, what's actually changing is the y-coordinate, because it stays in the same spot x-coordinate-wise. It just goes down below the axis instead of above. So that means that we change the sign of the y-axis. So to reflect over the x-axis, we change y. To reflect over the y-axis, the opposite, we change x. And that's how I remember it. Whatever axis I'm trying to flip it over, I change the sign of the other letter. So if I'm flipping it over x, I change y. If I'm flipping it over y, I change x. Now, we can also flip it over a diagonal line. Okay, this is the line y equals x. And if I want to flip it over this line, if I want to reflect it over to the other side, and I'm going to flip it over this line, what we can do is switch x and y. If I want to take this point and I want to take it over here, I'm going to switch their x and y coordinate. If it's the same line but going down, it's that y equals negative x. The rule is that I switch them and I have to change their signs. So I'm going to switch x and y, but I'm also going to make x and y the opposite sign. So these are 4 rules for how we change the points to do reflections over the coordinate plane. Let's put them into action. All right. So a trapezoid has vertices w, x, y, and z. Trapezoid w, x, y, z is reflected over the y-axis. Find the coordinates of the vertices of the new image. So there's a couple of important pieces of information here. We have our points. So we've got our 4 points, and that's useful. Here's the other piece of information we need. We are flipping it over the y-axis. I need to remember that when I'm flipping it over the y-axis, I change x. So that means I need to take these 4 points and I need to change their x coordinate. So negative 1, 4 is going to become positive 1, 4. 4, 4 is going to become negative 4, 4. 4, 1 will become negative 4, 1, and negative 3, 1 will become 3, 1. When you're flipping over the y-axis, you just change the sign of the x-coordinate. So those would be our new points. Don't forget also, when we talk about a new point, we use the prime. So if the original was W, the new point is going to be W prime. Here's another one. A trapezoid. This is the one we just did, but we're going to graph it so we can see what it looks like. Okay, so we graph the original, W, X, Y, and Z. And so there's our original trapezoid. But then if we graph those new points that we got for W prime, X prime, Y prime, and Z prime, look and see what happens. It is a reflection. It reflected it over the y-axis. Now notice the y-axis actually goes through the shape, but it can still be flipped. This point still ended up the exact same distance away on the other side. This point, 3 spaces away, still ended up 3 spaces away on the other side. So they ended up exactly reflected just by following those rules. Another one. A parallelogram has vertices A, B, C, D. The parallelogram is reflected over the line y equals x. Find the coordinates of the new image. So here's a key phrase. We're reflecting over y equals x. So we have to remember what is our rule for reflecting over y equals x. So the rule for reflecting over y equals x is to switch x and y. So that means for all of these points, for the new ones, I just have to switch x and y. I'm not changing their signs. I'm just literally switching their places. So for the new point, A prime, it's going to be 7, negative 4, instead of negative 4, 7. For B prime, it's going to be 7, 2. For C prime, it's going to be 4, 0. And for D prime, it'll be 4, negative 2. So that is the rule. You do have to memorize these rules. It will make your life so much easier. But they're not hard rules. You're not doing complicated math. So if we flip all of the points, we get our new points. And then we can actually look at a new problem. This one, same points. Notice we got the same points going on here. But this time, we want to reflect it over y equals negative x. That's a different rule. The rule for y equals negative x is that we have to switch x and y, so they're still going to change places, and we have to change the signs. So it gets all kinds of flipped around. We're going to switch them and change them. So first I got to switch them, then I got to change their signs. So this would actually end up being negative 7, positive 4. Because this had been negative, now it's positive. This had been positive, now it's negative, and they've switched places. So that would be A prime. Now switch places and change their signs. So negative 7, negative 2. Switched places, changed the sign. Switch places, change the sign. So negative 4, 0. Now do be aware, 0 doesn't really have a sign to change. So positive 0 and negative 0 are the same thing. Switch them and change the sign. So it'll be negative 4 and positive 2. So I switched their places and then I changed their signs. That's the rule for when it is y equals negative x. So we switch places and change the signs.